Sorry. Yeah. Okay, so the morning session, I derived this mean field dynamical model, and that's going to be the starting point of this lecture now. So we derived this mean field dynamical model. So I basically the two sort of standard kinetics are Glauber kinetics for or non it's called non-conserved order parameter kinetics NCOP, and the second one Kawasaki kinetics. So far we haven't talked about Kawasaki, but we've gone fairly to the depth of Glauber kinetics. So Glauber kinetics is also known as conserved order parameter kinetics. And again, Glauber kinetics applies for ordering of a ferromagnet, or for that matter, any problem where you have a non-conserved variable. And Kawasaki kinetics applies for phase separation of a binary mixture or any problem where you have a conserved order parameter. Two things you must keep in mind, basically. So starting from Glauber kinetics, I derived this mean field dynamical model. So it's obviously in the mean field approximation, and as the name suggests, and the mean field dynamical model is del. So Sk average is the order parameter. It's the magnetization, average magnetization at site K, and that's equal to minus Sk average plus, and that's where the mean field approximation was involved to make this tanh term tractable. Tanh beta j sum over the nearest neighbors of Sk, which I call Lk, SLK average plus beta h. Okay, so I think that's sort of important enough that we can put that in a box. And that is, as I said, the starting point for the second lecture. This contains the kinetics of the non-conserved kinetics of the Ising model, basically. Okay, and it doesn't matter whether it's going from non-equilibrium to equilibrium or whatever. It covers the whole sort of. It's derived under pretty general circumstances. Okay, and the nice thing about it is, of course, it contains a static solution. Okay, if you just say del by del t equal to 0, you find you get the correct mean field solution as the right hand side of this equation. Okay, I want to spend a little before we get into the solution of this equation. I want to sort of put it in a slightly more familiar form, which is the form of what's called the time-dependent Ginzburg-Landau equation. Okay, so that's now chapter 1, 3, and this is about the time-dependent Ginzburg-Landau equation. Ginzburg-Landau, and this is often known in the literature as the TDGL equation. I guess we all know the name of Landau, right? Of course, Landau is, I mean, apart from being a great physicist, also the author of this famous series of textbooks we've used.
You should also know Ginzburg as well. I don't know Ginzburg.
You know about Ginzburg also. Ginzburg was, I think, Landau's student, and I mean, probably at the time he won the Nobel Prize, he was the oldest person. I think he was 92 or something when he won the Nobel Prize. So,
99, right?
who? Kapitsa was 99? Oh, I see. I didn't know that. Okay, okay. So anyway, they had to wait, but finally, I guess that's a good reason to stay healthy, students. Keep that in mind. Okay. You have to hang in there till you get your Nobel Prize, basically. Okay. So anyway, so I'm going to reformulate this as the time-dependent Ginzburg-Landau equation, and this is a very nice and general formulation, which I hope you will have seen. But even if you've not seen, you should know this formulation because this sort of prescription of partial differential equations describing order parameters, that's a very sort of standard prescription in pattern formation. And the whole class of pattern formation problems fall into this category. So let's study this time-dependent Ginzburg-Landau equation, and that will then be my starting point for the solution of well, I should say the following. These equations are not exactly solvable in time, but I can get an approximate solution, and the TDGL version of it will be the starting point for the approximate solution. So what I'm going to do is now the following. Whenever you think of Ginzburg-Landau free energies, you should think of a coarse-grained free energy. So I'm going to coarse-grain this mean field dynamical model. And we all know what coarse graining is. We study it sort of in our stat tech courses. You basically have things defined on a lattice, and so that's a sort of discrete system. I've already gone to a coarse grained language out here. It's though the lattice is still underlying this treatment, but now I have an average order parameter rather than a sort of discrete order parameter. And now I'm going to actually go the whole distance and write this in terms of a spatial variable. And the coarse graining procedure basically associates the average order parameter here with a continuum point in space, basically. Right? So I don't really, I hope I don't need to repeat this. So my description is going to be from now on in terms of partial differential equations. And these partial differential equations are defined everywhere in space. And it's sort of understood that this is each point refers to some average over a few cells, over a few of the discrete cells. Okay, so I think the coarse graining procedure is sort of well, it's probably based on the days of Stokes equation, where you try to write down these PDEs. And the reason you try to write down PDEs as description of physical phenomena is because these are analytically somewhat approachable, right? As opposed to a discrete model, which is sort of analytically harder to sort of see. Okay, so that's the coarse graining procedure. And what I'm going to do is I'm going to identify this average order parameter as a space and time dependent order parameter. It depends on r vector, which is space and time t. Okay, and I'm going to sort of plug it back into this equation. So that's just psi. That's just psi again. Where I'm going to have to do a little work is out there. So let me try to write down this SLK in terms of psi. Sorry?
Can you increase the font size?
Okay, sorry. So I'll increase the font size. So now I'm looking at what's inside the tanh. So what I have inside the tanh is sum over LK, SLK average. And this is basically in continuous language, sum over the R vector of the nearest neighbors, and well, just psi R n at time t. And basically, the way you think of it is the following: if that's a point, that's the central point, then you have sort of neighbors in these two directions. So I'm going to Taylor expand this quantity around the central point, and it's clear. So if you do this in one dimension, for example, well, so you have the central point, and then you have a neighbor 1 and 2, and if you sort of Taylor expand it, what do you get? This is simply psi x plus a t, where a is the lattice spacing, plus psi x minus at, where a is the lattice spacing, right? So that's just a direct form of this sum out here. And these are the guys you Taylor expand. What do you get? You get psi xt. I'm writing the first one down, plus a del psi by del x, again evaluated at the central point, plus a squared by 2 del 2 psi by del x squared, etc. I'm just doing it on square lattice for simplicity. So that's the first term. And the second term is simply plus psi xt. Now, because the first derivative picks up a minus sign, so that's minus a del psi by del x. The second derivative goes back to the plus sign, a squared by 2 del 2 psi by del x squared. This is a standard sort of way of course trading. And basically, that's the sort of two expansions you get. And without any ado, you just cancel all the odd terms in the expansion cancel out, basically. Okay. So this sum or okay, so that's in one dimension. How about arbitrary dimension? Let me write down the result. Can somebody tell me what the result is going to be? So you're going to have 2 for each dimension, right? So for d dimensions, you will have 2d, q, just the number of nearest neighbors. So this is equal to, for arbitrary dimensions, q psi at the central point. And this guy is going to give me a squared del 2 psi by del x squared. The y direction will give del 2 psi by del y squared, and so on and so forth. So this is simply going to give plus a squared grad squared psi plus higher order terms. Okay, I'm doing it a little relaxedly, but whatever. It's sort of should see this done at least once, basically. Okay, so if I put this back into my mean field model, I get del psi by del t is equal to minus psi plus tanh. क्या हो जाएगा?
Sanjay, it would be q a square by 2, right?
Sorry?
Q a square by 2, the Laplacian one.
No. Each direction gives del 2 psi by del x squared.
Q such.
Then the y direction will give del 2 psi by del y squared.
Oh, sorry.
And that's why I've sort of combined it into this grad square, basically. Okay? Okay. So, okay. So, sorry, what was I saying? Yeah, so this is the first, this thing out here is q beta j psi. Let me not write down the argument psi xt anymore. Plus beta j a squared grad squared psi plus higher order terms plus beta h. Okay, that's the code. Just one. That's the mean field dynamical model written in the Costed language. Yeah. What's your question?
The arbitrary d shy of xd, and x is now a d-dimensional vector.
Yeah, x is a d-dimensional vector. Yeah, exactly. So, oh, sorry. Yeah, that would have been R vector. Okay. Yeah, I generalized to arbitrary dimensions. Okay. Okay. So that's my sort of expression for the mean field dynamical model. The last bit of calculation one does is expand this guy by a Taylor expansion. So you assume basically in all these Landau expansions, you assume you're close to criticality, and when you're close to criticality, psi is small, and then the derivatives are down by an order of the square of the correlation length, and then the fourth derivative is down by an order 1/4 of the correlation length, and the correlation length is going to infinity. That's the standard way how you justify a Landau expansion, basically. Okay, but keep in mind it's an approximation. It's not a sort of exact in any sense of the word. Maybe as t approaches Tc, you can justify it, but people freely use it at all temperatures, basically. This is often the case in physics, right? anyway, having said all that, let me Taylor expand this guy. So this is minus psi. Does anybody remember the Taylor expansion of catch Z? I want to give you a hint. It's an odd function. So I can tell you what the Taylor expansion is because I use this all the time. Tan Z is an odd function, so it's going to have only even powers, odd powers of Z. It's Z minus Z cubed by 3 plus higher order terms. Okay? As a homework problem, just do that Taylor expansion. It'll take you 5 minutes. Yeah. Okay, so then I'm going to sort of plug this in out here. So that's Q beta J psi plus, first I just get the linear term A squared del squared psi plus higher order terms plus beta H. Okay. And notice I've just deliberately written the higher order terms with just a sort of straight line because I'm going to just 1 minute. I'll answer all your questions, don't worry. So that's the linear term, and then the cubic term is just the cube of this, and this I'm going to write again in a very sort of arbitrary manner as the cubed plus more terms. Okay, this is very sort of ad hoc, the expansion, and is, as I said, maybe justifiable near the critical point. Okay, but that's often how phenomenology works. And plus, there's higher order terms in the Taylor expansion of that. Okay, so it's a whole mess of terms floating around, out of which very selectively Ginsburg and Landau are going to pick a couple of important terms. Yeah, there's a question back there. Yeah.
So what is the parameter A? Is it the lattice?
A is the lattice spacing. Yeah. I've just Taylor expanded around the central point. And
So we are told the coordinate picture.
yeah.
How does the lattice spacing come into play?
The lattice spacing, see, if I go to Taylor expand psi out here, I need to invoke this distance, right? So I have psi x plus at. That point is a away. You can just put it as 1 if you prefer, okay? If you work in units of the lattice spacing. And that's all I've done. That's the Taylor expansion. So it just gets buried into the length scale, basically. We use some microscopic scale to set the units of the length scale, basically. Okay? It's not part of the macroscopic model in any sense of the word. Okay, so that's, we're almost sort of at the end of Ginsburg-Landau's sort of derivation, if you would like to call it that. Let me make the last few identifications. Del psi by del t is equal to, help me out here guys, remember Qj is the mean field critical temperature, right? From Curie-Weiss theory. So this is Tc divided by T. Okay, so this is Tc divided by T minus 1 is the coefficient of psi. Okay, that's that term and that term. Okay, let's forget about h for the moment. Let's just write it down for h equal to 0. Okay, it's very trivial to write down for non-zero h. Okay, so let's forget about the h out here, and then I'm going to ignore all these other terms and only retain, or Ginsburg and Landau are going to ignore all these other terms and simply retain beta j a squared grad squared psi, and finally one cubic term only from here, which is minus 1/3. Qj is Tc, so that's Tc by T psi cubed plus a whole bunch of terms which have been ignored.
So Sanjay,
Basically, yeah.
T is the final Cohen's temperature.
T is the final Cohen's temperature and Tc is the critical temperature. Yeah, maybe I should have sort of remind you. I should have drawn this down. The magnet phase diagram is that and that. There's a critical point Tc, and by symmetry Hc is 0. This is a line of first order transitions. You have quenched from here to a temperature T, which is by definition of ordering problem less than TC. Okay, and it's actually, I can even go further and say it's far from TC as well. Okay, you don't normally quench close to TC. Okay, so that's now imagine if you had done that in the paper, the referee would have been all over you, right? Basically, but Ginsburg and Landau, it's okay. So they just happily ignore all the other terms, and that gives you the time-dependent Ginsburg-Landau equation, which is simply, well, I don't really need to write it down again. Let me just put this guy in a box. So though the derivation is a little sort of iffy, but this is a very important uh, equation in time-dependent phenomena. Okay, let me tell you what its other avatars are. So one is called the DDGL equation, the time-dependent Ginsburg-Landau equation, and the other name it goes by is Model A. For those of you who are interested in time-dependent physics, there's this classic reviews of modern physics articles by two of the stalwarts in the area, Hohenberg and Halperin. Okay, so I forget who comes first, but uh, Hohenberg and Halperin. This is an old reviews of modern physics article. Okay, I should maybe give you a little history out here, because most of you probably don't do critical phenomena in the sort of renormalization group sense of the word. First, there was static critical phenomena. The next set of things people studied were critical phenomena at dynamical critical phenomena at the critical point or near the critical point. Okay, so all these models are written down in what's called critical dynamics context, and they have the most unattractive names like Model A, Model B, Model C, which okay. But that's a standard sort of terminology. Okay.
How did you get the PC by T?
Huh?
How did you get the PC by T?
TC by T, Qj is TC in Curie-Weiss theory, and beta is 1 over T. And I just sort of cancel the AB, basically. Okay. And this also goes under the name of Allen-Kahn equation. Kahn equation. And quite simply, this is the standard model of pattern formation. If you look at a pattern forming system, this is the standard partial differential equation people write down in the context of chemical reactions, in the context of hard dynamics. I mean, you name it, any pattern forming situation, some variant of this equation arises. I quickly want to sort of add a couple of things here. I have taken a scalar order parameter psi, but the vector case is equally interesting as a matter of fact. Whether it's scalar or vector, it's model A by Halperin and Hohenberg. The two-component vector is the one that arises naturally in quantum mechanics, right? Because there you have a wave vector, you have a sort of wave function which is a complex quantity. Okay, so the two-component version arises in equations. Some variant of this arises in what's called the Grosz-Pitevsky equation of Bose-Einstein condensation. This is the ordering of the XY model. Has everybody heard of the XY model? And so on and so forth. The three-component version is the dynamical Heisenberg model. There you have a three-component spin, and this applies in the context of early universe kinetics of phase transitions. I hope you're aware of this. You would realize that the early universe is a very, very dynamic place, right? Supposedly there's this big bang and then things expand out, and there's all kinds of phase transitions going on in the early universe, and they're particularly kinetic in nature. And as a matter of fact, people use similar formalisms. They also have something called inflation and stuff like that. I don't want to get into that today, but they use similar formulations to study what's happening in the early universe. Okay, so again, that's the last sort of observation I'm going to make. Scalar and vector order parameters are studied. Okay, it's not just the scalar case that's of interest. Though for convenience of presentation, I will do the scalar case. But the vector case is actually much more interesting for reasons which I'll try to keep pointing out as I go on. No, I should say it's much more interesting. It's very interesting for reasons that I'll try to point out as we go on. Okay. So this, okay, I'm going to now sort of reinterpret this equation in several physically meaningful ways. Maybe I'll just leave the phase diagram up here because that describes the basic problem I'm interested in. The first way of thinking of this equation is the following. This is equivalent, and that's the formulation Halperin and Hohenberg use, to the following equation: del psi by del t is equal to minus some kinetic coefficient gamma, a functional derivative of a free energy, del by del psi, plus a noise term. Is everybody familiar with this formulation? Has anybody seen it? Okay. So then maybe seeing I'm not getting very many positive responses, let me just sort of spend a little time understanding it. Okay. The first thing is this is noise. And fortunately for us, so with noise you have a much harder problem. But fortunately for us, noise is irrelevant for most domain growth problems. And I mean irrelevant in the sense of as a relocalization group quantity. If you go to larger and larger length scales, noise becomes for most domain growth problems. Okay, so I'm not going to worry about noise anymore. The way to sort of motivate this free energy, yeah, please.
Some kind of what done? Some type of what done?
Some kind of it's exactly that. And that's what I was going to say next. Thanks for sort of pointing that out. If you're not familiar with this equation, I remind you about a particle. Let's just keep the simplest problem with coordinate x. Coordinate x in potential Vx. And of course, one usually writes down the Newtonian equation for this. The Newtonian equation, as we all know, is mx double dot is equal to minus v prime x, where the prime denotes a derivative. Okay? Everybody seen that at least? Newton's equation. If you have damping, you additionally provide the term minus xi, let's get our notation clear, xi x dot. The damping is proportional to the velocity, right? That's friction as a matter of fact. And in what's called the overdamped limit, basically what this equation does is the following is sort of, it's analogous to this one. In the overdamped limit, you can forget about mx double dot in comparison to that. You can drop the inertial term as it's called. Okay, this is what's called the overdamped limit. That's the phrase he used out there. And you can see that for a particle in a potential well, x double dot is minus v prime x divided by psi. What does this dynamics do? If you start the particle off somewhere, it basically dissipatively relaxes the particle to the local potential minimum. Okay? So v prime x has got to be 0, where the particle stops moving, and v prime x defines a minimum of a potential. To define a maximum of a potential also. Stops it to place the particle right at the maximum also, as a matter of fact. Yeah, I hope you're aware of that. Okay. And that's the analogy with which you write down this DDGL equation. The DDGL equation is an overdamped limit. Now, instead of x, you have a order parameter, which is space dependent. and this relaxes the order parameter to the minimum of the free energy starting from any point, basically. Okay, can somebody identify the free energy? Huh? Which can somebody identify the free energy which is going to give rise to this? Can you do a functional derivative in your head? Somebody? Should I write it down for you and then you sort of we'll sort of go by each term? Okay, so let me write it down. So the free energy is G psi. So it's a functional, so it's a integral of a function, right? I mean, we're sort of familiar with that notation. Is an integral over volume, and then the various terms are, let me write them down and then I'll sort of argue them. Half Tc by T minus 1, sorry. Half Tc by T minus 1 psi squared, and the second term is 1 over 12 Tc by T the whole cubed psi 4, and the last term is Tc by 2qt, where T is the temperature, E squared grad psi squared. That's the free energy which I claim gives rise to that particular equation. Let's just confirm that when you have normal polynomials in psi, the derivative, functional derivative is just like the normal derivative basically, right? So this guy is going to give a 2 factor, ये इससे कट जाएगा, ये वाला term आ जाएगा minus sign के साथ. Well, absorb the gamma into the time से, and इसका डेरिवेटिव लोगे तो 4 आ जाएगा, तो 1/3 ये हो जाएगा, ये वाला हो जाएगा with a minus sign, and the only place you have to do a little effort is to take the functional derivative of that psi squared. Okay, and that's what I want you to sort of go home and sort of try to. If you haven't learned it, dig it out on the web. Functional derivatives, if you're going to be a theoretical physicist or any physicist, you should know how to do functional derivatives. Okay, basically. Okay, and what is the nature of this free energy? It's got a local term, which is just the Landau term, and then it's got some kind of surface tension penalty on the variation of the order parameter, basically. Okay, if the order parameter varies in space, it costs me some energy, and that's usually known as the Ginzburg term. I should tell you that Ginzburg and Landau first wrote this down, I think, in the context of formulating a phenomenological theory for, I forget, type 1 or type 2 superconductivity, one or the other. Huh? The reason I'm spending so much time on this is because these free energies are very important in all branches of time-dependent physics. Okay, so you have a local term and you have a surface tension penalty. Okay, what does the free energy look like? Can somebody help me out here? Let's just plot the local part. So let's call this local part G psi, and forget about the surface tension energy. What does G psi look like? I need some help from you guys. G psi as a function of psi, what does it look like? Somebody tell me. For T greater than Tc, what does it look like? It's going to be, you have two very distinctly different forms for T greater than Tc and T less than Tc. Huh? It will just be a bell-shaped parabola. And let me again stress this idea of universality. What's important here is that even if you have a sixth order term, it doesn't matter. That form is going to be approximately the same. And the minimum, so that's for T greater than Tc. And the system comes and sits at the minimum of the free energy, which is located at psi equal to 0. That's the minimum order parameter that corresponds to 0 magnetization. What happens for T less than Tc? That's very crucial. For T less than Tc, this guy is negative. Okay, So at small psi, you can forget about this term. So it's a downward parabola. Okay. So it's a downward parabola. Very different, huh? And then finally, as you go to larger psi, the psi fourth term stabilizes the free energy and goes up like that. That's for T less than Tc. Okay. Where do the minima now sit? The minima of the free energy now lie. So psi equal to 0 has become a local maximum. Now the minima sit at this non-zero values of free energy. One is minus psi 0 and one is plus psi 0. Okay. And this is what was given this beautiful name of broken symmetry. The symmetry is broken under the phase transition, under the critical temperature. What is my kinetics of phase ordering problem in this language? I start off with this potential because T was above Tc. I had the paramagnetic phase sitting down here. Now suddenly I quench T below Tc. So the free energy becomes like this. So the order parameter which was sitting out there will now go into either this fixed point or into this fixed point. It's equally happy going both directions. Okay? And obviously what is going to happen is it's going to go both directions to start with. And then finally as time wears on, one phase or the other has to be down, basically. Okay. So that's, I mean, remember this term, broken symmetry. My advisors used to say, whatever else you do, if you want your work to be really well known, you come up with a good name for your work. And broken symmetry is right on top of the list of good names. Okay. So you have to think up a very nice, catchy name for the sort of physics you're trying to describe. Why is the symmetry broken? Can somebody tell me? What is broken up here? These are very sort of, huh? What is broken? The up-down symmetry is broken, right? In the paramagnetic phase, whether you look at a frame of reference up or down, the system looks the same. In the broken symmetry phase, looks different if it's an up axis versus a down axis. What is more symmetric, a liquid or a crystal? Answer that, huh? Liquid. Why? Huh?
Every point looks similar.
Well, that's not a very mathematical statement. Make a clearer statement.
It is translational and rotational.
It has continuous translational and rotational symmetry in a fluid. In a crystal, you have only discrete rotational and discrete translational and discrete rotational. Less symmetry. Always keep this in mind that the ordered phase in all these systems breaks symmetry and it's lower in symmetry than the disordered phase. Okay, I mean this is a diversion, but worth taking nevertheless. Okay, so for T less than Tc, the extrema are determined by G prime psi is equal to 0. That's where the extrema lie. Notice I'm not using the word minima. And that gives me the equation minus Tc by T minus 1 psi plus 1 by 3 Tc by T cube psi cube is equal to 0. And what are the solutions of this? One of the solution is psi equal to 0. So one of the extrema of this free energy is psi equal to 0. But that's an unstable extrema, right? Psi is equal to 0. And what are the other extrema? They are symmetric extrema located at plus minus square root 3. Let me write down the exact expression, though this prefactor doesn't matter. It's Tc by T raised to the power 3 by 2, Tc by T minus 1 raised to the power half. That second term is what matters, and that has what's called a cusp singularity at Tc. Okay. So the kinetics of phase transition problem is I start off at psi equal to 0 plus fluctuations. I end up on either of these fixed points or both on these fixed points as a matter of fact. Okay. Are there any questions at this point? Any doubts? Huh? So let's get back to understanding the dynamics of my TDGL equation. That's the TDGL equation. I'm going to put it now in a dimensionless form. And the dimensionless form, I'm not going to do the effort out here. But basically, you have to identify the dimensionless form. I'm going to leave that as a homework problem. Actually, it's given in some PDF I'm going to circulate. But nevertheless, work it out as a homework problem. You have to identify the natural scales of time, space, and the order parameter. Rescale those quantities out. And finally, you get a dimensionless equation. Del psi by del t is equal to psi minus psi cube plus grad squared psi plus h. This is the fundamental equation of kinetics of phase transitions. It's called I call it the TDGL equation. Others use different names. And the problem I want to solve is psi going from 0 to these non-trivial fixed points. Okay, how does that happen in time, basically? And I've already told you that this equation is not analytically tractable. That should not be a surprise because it's a nonlinear PDE. It's nonlinear and it's dissipative. And in general, you know, not even nonlinear ODEs are tough, but nonlinear PDEs are hopeless to solve. Basically. Okay, so not surprising. This is not analytically tractable. But the question is, as a theorist, one still wants to make statements, and it turns out one can make very non-trivial statements about the kinetics of phase transitions as described by this equation. Okay, so that's where I'm going to go next. We have 2 minutes for questions if there are any. Huh? Okay, so let's try to understand what this equation does, but let me get some space on the board. So whenever you're confronted with a nonlinear PDE in your research, the first thing you do is find the fixed points. Okay, and the second thing you do is do a linear stability analysis around the fixed points. Okay, that's already going to give you some flavor of what the system is going to behave like in time. Okay, so what are the fixed points? So let's again just as I said, with H turned on, the problem is actually not particularly interesting. You just go to the preferred phase. So I'm going to set the magnetic field to 0. Okay, that's where you have coexisting phases. What are the fixed points in this dimensionless language? Where does the dynamic stop? The fixed points are obtained by putting del by del t equal to 0 and grad squared equal to 0. Huh?
Why we said grad squared?
Because it's a homogeneous solution. The fixed point is where if you reach the order parameter reaches that value, it stops evolving out. Okay. So what are the fixed points? Can you tell my inspection? Sorry, the fixed points in the dimensional language were this. What are they in the dimensionless language? So psi equal to 0 and plus minus 1 are the fixed points of the dynamics. And these are very important in analyzing this nonlinear PDE. Okay. Recall 0 is an unstable fixed point, and in the parlance of nonlinear dynamics, plus minus 1 are stable fixed points. It's like if you have a pendulum, you know, pendulum not suspended by a string but by a rod. If the pendulum is vertically downwards, that's a stable fixed point. If you displace it from there, it comes back to that point. On the other hand, if the pendulum is standing on its head, that's also a fixed point. But if you displace it from there, you go far away from the original state. So that's unstable fixed point and that's a stable fixed point. Okay. So let's go back to my kinetics of phase transitions problem and try to sort of understand what this equation is going to give me. Okay. So now I'm back to my APT problem. I made enough statements about equilibrium. In my APT problem, I start off with, yeah, if I can find it here, I start off with my TDGL equation with psi equal, at high temperature, psi is equal to 0 and plus minus thermal fluctuations. Okay. So if I want to describe it in the TDGL framework, psi R0 is equal to 0 plus small amplitude thermal fluctuations. If you don't put in the fluctuations, you won't have any dynamics at all because 0 is perfectly happy to be 0. It needs to be slightly displaced from 0 to do something, and that slight displacement is provided by thermal fluctuations. Only the initial condition, right? So that's the dynamics. What would be the counterpart? I just want your students to tell me what would be the counterpart in the Glauber-Ising model. What would your initial condition be if you did a Monte Carlo simulation of phase ordering? You start off with a paramagnetic phase. What is a paramagnetic phase in the Ising model? Huh? N तो है ही नहीं ना वहाँ. You have spins which are either +1 or -1. So what is the initial condition? Average है ही नहीं वहाँ. You just say discrete spins which are either plus or -1. So you have a lattice. The corresponding initial condition in the Glauber-Ising model is a lattice which spins plus or -1 randomly. That's your initial condition. Okay. After the quench, you're going to have to ask how the Monte Carlo simulation evolves that initial configuration, and the descriptions are the same. So maybe I should write this down in the corresponding. After all, these are just two descriptions of the same reality, basically, right? So in the Glauber-Ising model, initial condition is sorry, we don't have a psi out there. The initial condition on the field SI at time t equal to 0 is plus or minus 1 randomly chosen. That's what a paramagnet looks like. Okay, and then you quench below the critical temperature, you do a Monte Carlo simulation, and then you see what will happen. But anyway, let's get back to our TDGL problems. What you do with this initial condition, let me call these fluctuations, let's give them a name. Delta psi, delta for small, are 0. Let's plug these into the TDGL equation and see what we get. Del psi by del t simply becomes del by del t of delta psi. And this becomes psi 0. So that's just delta psi again. Psi cubed is delta psi cubed. In a linear stability analysis, you can forget about it, right? That's why you have small fluctuations. So I'm going to forget about that. Plus del squared delta psi. That's what happens to the initial fluctuations. Okay. You take a Fourier transform both sides, and you know that you get del by del t of delta psi. I'm just going to use the same notation, but the argument indicates that it's in Fourier space. The argument is of k vector. That's equal to, this still gives you again a delta psi kt. And what does the del squared give you in a Fourier transform? Minus k squared. Okay. All those of you who have not seen that, please work it out. A squared delta psi kt. Okay. That's the simplest of equations to solve. That's just 1 minus k squared delta psi kt. So in Fourier space, it's nice and simple to solve this equation. And you can see what the solution is. delta psi kt is equal to t raised to power t 1 minus k squared delta psi k 0. That's the growth of initial fluctuations in the linear stability analysis. Okay, obviously the linear stability analysis will only be valid as long as delta psi is small. Okay, so what are these initial fluctuations doing? This is normally called lambda k in the literature. The time scale of the growth of fluctuations depends on the wave vector, and it's very straightforward to plot lambda k. Lambda k as a function of k, lambda k as a function of the magnitude of k is its maximum at k equal to 0, and then it sort of goes down as k gets larger and then finally goes negative. So all modes with k less than what value? 1. All modes with k less than 1 are unstable. I want you to have a picture in your mind. You're starting off with this paramagnetic phase. You have small fluctuations about 0, and the fluctuations with k less than 1 in Fourier space are going to get amplified with time. Okay. What happens as they continue to get amplified? If they get amplified forever, they'll become infinity. What saves you? What saves you? How does this equation make sense? Students? The non-decay term rescues you. Once the fluctuations become too large, then they are saturated because there's a minus sign by the nonlinear term. Okay, so this is called a saturation. And again, this is simple. It should be simple stuff, but I'm emphasizing it because this is a very generic formalism of pattern forming systems. Okay, linear instabilities are amplified, and then they get saturated by some nonlinearity. Have you all heard of the Turing instability? Huh? Go check it out on Wikipedia. Do you know the name Turing at least? Turing, everybody knows, I hope, right? He's a sort of great man in computer science, theoretical computer science. The Turing instability is basically a generic formalism for pattern formation. I think he did it in the context of coupled cells, but yeah, the application he had in mind doesn't matter. What matters is that he laid out a framework for how to study pattern formation in an initially homogeneous system. To divert for a minute, but just to sort of emphasize the point, pattern formation is very universal in nature. You have a human embryo, for example, you start off homogeneous, and then sort of there's an instability, fluctuations, growth, something becomes arms, something becomes legs, something becomes head, and so on and so forth. So imagine a more beautiful example of pattern formation. Or you have a zebra born without any stripes, then there's some instability of the skin of the zebra, some chemicals sort of undergo fluctuations which amplify and get saturated to set the length scale of the zebra skin. Yeah, so these are all problems in the same category. So what happens schematically, if I plot delta psi RT as a function along, let's say let's plot it in x one dimension x. So you start off with small fluctuations here. Some of the modes are getting amplified, not all the modes. Some of the modes are getting amplified exponentially, as a matter of fact. So they won't grow regularly. They'll grow something like that. Then at a later time, it will become something like that, like that. Okay. And finally, the nonlinearity kicks in, and you saturate at the equilibrium fixed point value and your structure becomes as so at late times. You saturate, remember you are equally happy to be either of the fixed points. So you saturate, some regions saturate at -1, some regions saturate at +1, and then these domains grow with time. That's when domain growth starts. Once this nonlinear amplification of instabilities is done, domain growth process starts, and then it makes sense to talk about the length scale of these domains and so on and so forth, how it grows as a function of time. Intuitively, you can tell that the interfaces, the system has interfaces, but it doesn't like them. It doesn't like them because they cost me grad squared, psi squared in energy, right? I have to pay a surface tension cost. So my goal as a system is to remove the interfaces to the extent possible. And this process of the interfaces colliding and coalescing and domains and things becoming larger and larger is what's called the domain growth process or the coarse-leaf process, because the length scale of these domains grows with time. And at the end of the day, you will have a single domain in a finite system, all +1 or all -1. Okay. So then at that point, you have no interfaces. Okay. It's going to be very different in the phase separation problem, but that will come later. Okay. Well, not very different, it will be different in the phase separation problem. Okay. So then again, let me reiterate, the initial instabilities get amplified. They get saturated by nonlinearities to their equilibrium domain values, which in my dimensionless language are ±1. And those domains will then grow with time to reduce the surface tension energy and thereby get rid of this term and make psi homogeneous everywhere. Okay. Okay. Are there any questions at this point? Any doubts? And this is a generic scenario in pattern formation. All sorts of systems, chemical turbulence, etc., you name it. Bird feathers, I mean the works. Everything shows something on these lines. Okay, so that's why I took this dimension society. Yeah.
How is the surface term reduced?
How does?
How does the surface term is reduced?
The surface term is what I'm coming to next. But if you have grad psi, you pay a cost for it. And grad square psi squared मतलब positive ही cost हो सकता है, negative cost नहीं हो, right? So if you can remove the grads in psi, i.e. make the system homogeneous, then you finally drop this term out.
So width of this interface is right, correlation length. Width of the interface.
Yeah.
That is the correlation length.
Yeah. Well, it's actually the correlation length in the dimensional units.
Mm-hmm.
In this unit, it's just a number.
Right. Okay. So how to calculate the time scale and how long it take to go to the final state? Yes, in this problem.
We'll get to that. Well, as I said, in an infinite system, this pattern formation process will continue indefinitely. You'll just have larger and larger domains alternating between plus and minus. And those have a length scale. Okay, I can tell you the answer actually. Generically, the length scale goes as the square root of time. The picture you should have in your mind is that these interfaces perform random walks, and then they have a collision time. But then they collide, they merge, and then larger interfaces take longer to merge, and so on and so forth. So the system size goes, the domain size goes as square root of t. That's generic in a random walk, right?
Right.
Okay. And L square goes as time t. If you have a finite system, that will stop when this becomes comparable to the system size.
But this size that you define here is noise average, right? I mean, essentially, you take average of the noise, and then if the mean is 0,
Yeah.
then you get back this equation. So it's noise average or noise is ignored?
No, noise ignored, because it's actually irrelevant for most domain growth problems. See, you have these bulk, okay, maybe I can tell you why it's irrelevant intuitively. You have these bulk domains being formed, okay, and you have these interfaces. If you increase noise, the bulk domains stay bulk domains. All that happens is the structure of the interface changes. It becomes softer.
Yeah.
But the width of the interface ultimately becomes irrelevant compared to the domain size.
I see.
So, if you increase the temperature, the width of the interface grows, but the domain size, it's a fixed constant larger value, but the size of the domains grows, it finally makes it irrelevant.
But it is true only the surface tension is sufficient height that if the tension goes to zero, like in surfactant system.
Then there would be no reason for this growth to.
Okay.
The growth is driven by
Okay.
surface tension. Exactly. In forms, etc., it's driven by surface tension. Okay. Yeah. But
We started off with the paramagnetic field, right? So now, as we come to this domain, so now for psi equal to +1 and -1, they correspond to all spin up or all spin down. Right? Now the domains are growing for both +1 and -1. So how does it then propagate to either one of the bands?
that's the breaking of symmetry, finally. The phase transition is complete when you break symmetry. If you do this experiment 100 times numerically, half the times plus will win out, half the times minus will win
So
out.
after some time, it will saturate by.
But again, and that's a question Purjapat asked, only the infinite system will saturate. In a finite system, sorry, that's not correct. In an infinite situation, this pattern growth process will continue forever. The saturation to one single domain is a finite size effect of the system.
For finite size, it will saturate.
For finite size system, well, forget about the finite infinite size. These guys keep growing with time and finally saturate at either +1 or -1. That's a good enough.
So it's actually X has a limit.
Yeah. That's if X doesn't have a limit, then this process will, it's a sort of time dependent state that it will fall. Okay.
T to the power half is in all dimensions.
T to the power half is very generic as a matter of fact, but it doesn't apply in 1D. In 1D, the growth domains actually have logarithmic growth. And there's a reason for that, which maybe I'll flesh out in the next few minutes. But for all dimensions greater than 1, you have t raised to power half. For all vector order parameters, and this is something Alan Bray and I sort of found, the same t to the power half law applies again.
But from
Except, sorry, so if you look at the ordering of the xy model, where psi is a vector, then again the appropriate defects are vortices in that case. The vortices, anti-vortices, annihilate, grow, become larger and larger, and there the length scale is again square root of time, except in 2D when the vortices are point defects. The vortice is sort of a bunch of arrows around a circle, and then it's a point defect. Then you get a logarithmic correction. That's what we found. But generically, it's t raised to power half in the non-conserved case.
you said in 1D it's logarithmic.
In 1D, it's logarithmic period, huh?
Greater than one dimension
It's t raised to power half for the scalar TDGL equation. For the two-component TDGL equation, which describes the ordering of a superconductor, the appropriate defects are vortices and anti-vortices. These defects move around here, collide. There the vortices and anti-vortices move around, perform random walks, collide, coalesce, and the growth process takes place. There the growth law, in 1D you can't have a vortex, you can deform it away topologically. In 2D, above 2D, it's t raised to power half, again, the same growth law. In 2D, where the vortices are point defects, there you have a logarithmic. We've cataloged all these growth laws. It's complicated, yeah. As I said, at least for the non-conserved problem, we have a pretty good understanding. Even though it's not analytically solvable, we have a pretty good understanding of it. Yeah.
So when we are mentioning this growth law, T to the power half, we have to both mention that it's the non-conserved case and also it's regards to the scalar order parameter.
Yeah, I think if you make the generic statement that T is raised to power half, that's a good statement. Logarithmic corrections and all very fussy guys can worry about. You can make the statement that it's T raised to power half. Okay? in the non-conserved order parameter case. In the conserved case, which we'll discuss tomorrow, it's going to be much harder, okay, to find the growth law, and it's much slower as a matter of fact. Not much slower, it's slower as a novel. Okay. Okay. Any other questions? Do you want to summarize? Maybe I got too confusing. So for the scalar case, is t raised to power half for d greater than 1, and ln t, obviously you have some time scale out there, tau for d equal to 1. Okay, in 1D these are just again point defects basically. There's just one point at which you have an interface. Okay, so that's the scalar case. For the XY model, LT is t raised to power half for d greater than 2, and if I remember correctly, it's p ln t. I can check this. Raised to power half for d equal to 2. We did this a long time ago. Okay. And for d equal to 1, it makes no sense to talk of an ordering problem of the XY model because the defects can topologically be removed from the system. You don't have a defect if the dimensionality is less than the order of the order parameter. Okay. In 3D, you have monopole defects. In 3-component case, you have monopole defects. Those arise in the ordering of the universe and liquid crystals, the ordering of liquid crystals. And then again, generically, it's t raised to power half. Okay. Okay. The last I have, particularly, I should end here. We already have, yeah, we just have about 10 minutes left. The last thing I wanted to do was derive the kink solution, the interface solution. Whenever, see, for all finite time, you have this structure of domains. Huh? So the next thing I'm going to do is derive another solution of the PDGL equation, another static solution, which is this very famous kink solution. Kink, domain wall, whatever you want to call it. Huh? Solid on, instant on, all sorts of things are there. Okay. So should I derive it tomorrow or should I derive it today? Let's derive it tomorrow. Mera bhi gala thak gaya, huh? But I can answer questions if you have any.
Yes, we have some questions.
Yeah, but maybe the audience wants questions. First, okay.
No, there wasn't.
First from the audience, and then
This derivation of the kink, I mean, it's quite straightforward. Maybe you guys try it overnight just for the heck of it. Look for a static solution of this guy, but now insist that it goes to +1 at one end and -1 at the other end. That's what's called a kink. Okay, and thereby you can figure out. Obviously, the kink solution is going to be higher in energy than the homogeneous solution. You already know that. But it's just a little higher, and that's why these kinks are reasonably stable. Okay. And especially if you set boundary conditions where you insist that it's +1 or -1 at different ends, then you can't get rid of a kink. It's a topological defect which is there forever, basically. Okay. These kinks will play a very crucial role in our understanding of phase ordering. Okay. Because these are the sort of profiles between domains. Inside the domain, everything is relaxed. You are in equilibrium, you are happy. You're only unhappy at the interfaces. You want to remove the interfaces. So, and let me already say what's going to come next. We're going to capture the kinetics in terms of what these defects are doing, basically. Okay, that's the handle we use to get an analytical feeling for the growth laws, etc. Okay, but I should answer the questions. Yeah, there are any more.
What is it LT defined as?
LT is the typical size of this system
Is it
at time t. Obviously, every domain doesn't have the same size.
for finite system? It will remain finite.
No, even for infinite system, it will be finite. It's just the size of the domain, and it grows with time. A typical domain. You started off with no domains at all. As time goes on, the domains are growing now, and they're growing as a square root of time.
If you take a finite system, there is a restriction on the length, right?
Right. So this, when you hit that length, you stop growing.
It will hit that, it will reach that length by this law.
Yeah, yeah. There may be corrections when you are very close to the overall size of the system, but this applies pretty much till the end of the process. Okay. So that's, yeah. I'm actually glad you asked that question because you might think this is all theoretical, whatever, but it's actually when you know the experimentalists, they don't look at the correlation function. Theorists, numerical guys like to look at correlation functions. The experimentalists actually look at the structure factor, which is just the Fourier transform of the correlation function. So when you shine a beam of neutrons or light or whatever your favorite probe is on a system, you pick up a structure factor. You must have studied this in your quantum mechanics scattering course. And the structure factor peak is proportional to the inverse of the length scale. So that's how the experimentalists calculate it. They shine their beam of favorite probe upon the system, pick up a peak, and the peak measures the characteristic length. Correlation functions are experimentally probably not measurable, actually. Or at least you can measure their Fourier transform, so you can. Yeah.
So for finite system, it's with probability 1, the system will ultimately give to all spins up or all spins down.
Yeah.
But in
You don't.
infinite system, that will never happen.
That's a good question. You're asking whether you can get trapped in a metastable state with one kink or something. One kink, or you can't get trapped. Your periodic boundaries, you have to have at least two kinks, right? And this process becomes really slow as they become apart in 1D. Because as you will find when I actually derive the functional form of these kinks, there's only an exponential of this 2 kink solution differs from the 1 kink solution only by an exponential correction in the tail. Okay, so essentially this is 2 independent kinks when they get apart. There's only an exponential correction. And the exponential correction is what gives rise to the logarithmic growth law. And for you can't numerically drive a system to all up or all down most of the time.
No, so then for finite system, after L square time,
Yeah. Now, L squared in 2 dimensions. In 1 dimension, e raised to power L. E raised to power L, yeah, because it's logarithmic.
okay, very slow.
Yeah. But I think their theorems, mathematicians have worked on this equation and they say, I don't know, obviously they can't make a statement that the dynamical evolution will evolve to the all up or all down, but they sort of estimate the times it will take to reach the final state.
No, so in 1 dimension, I mean, it's a deterministic equation. How do you argue that it's not? I mean, it's a simple argument.
Well, yeah. The argument is the following. When I derive these guys, well, maybe I can already tell you what you're going to find. You'll find that the kink solution is tan hyperbolic z over, I think it's in my notes, but I think it's square root 2. Okay. So if you're along the z-axis, if you plot the tangent pops up a lot in this, I guess, yeah. So basically the kink psi kz, in this language, that's a kink, goes from +1 to -1 over a length scale of square root of 2. And the anti-kink goes from +1 to -1 over a length scale of square root 2. That's the sort of typical correlation length in these dimensionless units, basically. Okay. So if you have another kink far apart, so this part changes is different from 1 by only an exponential quantity, e raised to power minus z. If you have 2 kinks spaced apart, they differ from this plus that, and that's what drives the growth. They differ from this solution plus that solution only by an exponentially small piece. And if you write the dynamics in terms of the minimization of that small piece, that's where you get the logarithmic law. Maybe I'll derive it tomorrow. Okay. But I hope intuitively Get the logic, huh? So typically this is a one king problem. There you can for branch you can easily find out how much it differs from one, and you find it exponentially saturates to one with a e raised to power minus z, basically. Huh? And if you have another kink there, the overlap of the two kinks is, if they're far enough apart, is only by e raised to power minus something, and that's what gives the logarithmic.
So this power half, is it a consequence of overdone dynamics? You're taking the underlying dynamics from overdone. Is it because of that?
Yeah, because in a underdamped dynamics, here you don't have the possibility of oscillation.
Yeah.
In an underdynamic damped dynamics, you would have overshoot and relaxation back. I don't know whether it would change things substantially, but people normally don't study the underdamped case. That may be because Halperin and Hohenberg in critical dynamics always used the overdamped equations. और the model A, model B, C, D, E, F, कुछ क्या नाम रखा है. They are all overdamped.
And the logarithmic dependence.
Yeah.
And the got anything to divert of the hydrodynamics in 2D or 1D depending on the.
No,
It's not.
no, it's not the same. It's as I told you, just very simply,
Okay.
how much does this kink overlap?
With the other.
Overlap means how much does this tail differ from the sum of two individual kinks? Because that's what gives you the potential to drive the distance between the two. And that's a very small factor, becomes smaller, exponentially smaller as the distance becomes further apart. Yeah.
How is the domain reflected in that data?
So in the free energy diagram we did, you start off here. That's your initial condition, the paramagnet. Okay. Part of the system falls into this. Part of the system falls into this.
So we are already at T less than this.
Yeah, but at some geographical points, if you had negative fluctuation, you will fall into this guy. If you had positive fluctuation, you fall into that guy. Okay. So then you establish a solution between this and this. That's the kink which I'm going to derive. Also known as an instanton in field theory. Okay. Or a soliton or whatever. All sorts of names. And then the system domain grows by eliminating these kinks.
I think she was asking about in terms of this free energy diagram, can you describe the coalescence? The population of one minimum is
No,
equal to the
no,
other.
it's because this is I haven't put the del squared psi in here, right? For that, I would have to plot it as a function of field. This is just a function of the homogeneous order parameter. Exactly, but I mean, कैसे करेंगे? Infinite, the field is infinite. Define an infinite domain. That's hard to see. But the picture you have in your back of your mind is in phase space. You are moving downhill in free energy. Downhill not to be associated with this downhill, but overall you're moving downhill in free energy. And that's what the overdamped case always does. It dissipates you to the minimum of the free energy. Dissipating. You don't overshoot and bounce back. Okay. Actual pendulum, of course, you overshoot and then. I mean, if you have dissipation, it sort of keeps overshooting and then finally relaxes back to it. Right? Yeah.
The number of domains. Suppose you start with a contribution, you count the number of domains. Will the number of domains monotonically decrease?
Yeah.
Monotonically.
Yeah. As a matter of fact, the number of domains is an inverse measure of the length scale. The length scale goes as L of T. Then see, much of the region.
So your new domain.
If this is a volume V, much of the region is occupied by domains. So as L grows, the number of domains has to come down. And it's just the inverse. Yeah.
A new domain cannot be created within an already existing domain.
No, no. I mean, there are some experiments which show what's called double phase separation, but that's too offbeat. I mean, we will just do bread and butter stuff. Okay? So once domains are formed, they're there and then they grow. Yeah. In nucleation, of course, things are little. Yeah.
That is why the stripes of zigzag. Otherwise, it would be spots.
Yeah. But I mean, again, the zebra is not quite this guy because the zebra, okay, how to put it? I mean, zebras are of great interest to us. So, I mean, not just zebras, leopards, tigers, and so on and so forth. I think there what happens is you have what's called a mesoscore scale ordering. This guy is the simplest ordering problem. It goes all the way to infinity. There, something sets a characteristic length scale of the stripes or the spots or whatever. Little more sophisticated. I mean, the zebra doesn't want to be all black or all white, right? Would help with mating and all that, probably, right? So it wants its stripy. And there's some more physics you have to put in. You can build up a free energy more complicated than this. This was, I forget who other guys who did it, but it's a very famous piece of work actually, but I forgot the names, where you actually have the lamellar structure as the equilibrium structure. So I mean, first approximation, the zebra is lamellar, right? But in this case, the lamellar structure is not an equilibrium.
No, so then zebra stripes cannot be produced in equilibrium condition, like using a free energy.
No. That's not what I said. Zebra stripes are the minimum of a more sophisticated free energy.
Oh, I see.
Yeah.
There is a phase description.
There's a free energy. Maybe I'll dig out the name overnight. There's a very well-known guy, some Russian guy wrote down this free energy. Whatever. So then, I mean, you have lamellar structures, not just in zebras, in Rayleigh-Bénard convection. This is this famous experiment where you have two plates of different temperatures and you have these convection rolls, and depending on the temperature gradient, you can have convection rolls and all sorts of structures. This is described by what's called the Swift-Hohenberg equation. The Swift-Hohenberg equation actually has lamella as its equilibrium structure. This free energy can't do it, though. You have to have some more
right. Yes.
spatial dependent stuff. I can give you a physical example if you want. Think about what's called a copolymer. Okay, a copolymer is a jointed A and B. A and B like to phase separate, but now because of the joints, they can't phase separate forever. So they have to stop and form some equilibrium structure, which is lamellar, or it depends on the proportion of A and B.
No, but say there are two species, A and B. So now, say from the microscopic point of view, I mean, what is the kind of interaction you put in? Short range interaction, I don't think would do.
It's not a short range interaction. It's from the long range interaction. And if you Google this, you'll find hundreds of papers, because in thin films, they have all these patterns which actually stop growing at a characteristic length scale. So that's yet another length scale in the system, the saturation size of the domains. And the zebras fall into that category.
Yeah, recently actually there was a paper by Dickman and Raul and Gas or something.
Dickman.
Dickman, yeah. So they actually reported this kind of lamellar phase, but in the non-equilibrium condition. Okay, I did not know that in equilibrium condition.
You can have an equilibrium free energy which gives you a non-linear lamellar phase. Yeah. Swift-Hohenberg equation is an example. There's something called the Swift-Hohenberg equation. It has a fourth derivative in it, whatever. But if you just search for the Swift-Hohenberg equation, that has an equilibrium free energy with a long-range interaction term, and the long-range interaction term gives rise to lamellar structure.
Okay. So maybe quickly we take questions from here. So
two questions from Anish Acharya. Why did you discard the gradient term in the small g/psi? Why did you discard the gradient term in the small g?
G shy, I wanted to ask.
Anish, I was just plotting G psi, that's all. Okay, so for a homogeneous phase, I just plotted G psi, that's all I did. Okay, the gradient term is very much there, as a matter of fact, that's what drives domain growth. Okay, I just plotted the homogeneous free energy just to give you a flavor of what symmetry breaking and what the sort of mathematics underlying the domain growth process is. Okay,
I see. It's just for the simplicity.
It's very much there, the grad squared term, and it's essential because otherwise you don't have surface tension in the system, and then you don't get domain growth at all. Okay?
Yeah, sure.
In this series expansion of TDGL in the RHS, up to what order terms we should consider?
Okay, I mean, I didn't do the series expansion. As I said, if I'd done it, probably the referee would have thrown it out. Huh? The way it works is, again, this is Landau wisdom. You keep the minimum terms which give you the right physics. Okay?
Okay. Yeah.
So obviously that's a function of the physics you are targeting. But this is the principle of what's called a minimal model. You make it as simple as you can without discarding the physics. Okay?
No, shouldn't we specify that the higher order terms may not give new physics, or those are neglected, kind
Yeah.
of?
So, well, like for example, you can see. I mean, maybe I shouldn't be so flippant about it. But if you put in a psi 6 term into G psi,
Yeah.
okay, psi 6 will not change the symmetry breaking shape of this free energy at all. Okay.
Okay.
So psi 6 doesn't matter, but it does matter in some problems. It doesn't matter for the ferromagnet. But suppose the fourth order term goes to a negative sign, then you need
Yes,
the sixth
exactly.
order term to stabilize the free energy. And that actually happens in liquid crystals and so on and so forth. Okay. So when you write down a Landau expansion, the sort of thumb rule is the highest term must stabilize the free energy at large values of the order parameter. Okay. Whatever
Okay.
that higher term need be.
I see.
So typically people don't study more than sixth order. I mean, I don't think there are any applications of eighth order Landau free energy. Huh? But sixth order is, I mean, the liquid crystal literature is full of sixth order free energies.
So we should stop at the term where we can stabilize the
Where the free energy is stabilized, i.e., the last term in the free energy that you keep should have a positive coefficient.
positive
Yeah.
coefficient. Yeah.
And it should not have the possibility of changing sign. That's the sort of thumb rule for a Landau expansion. It's a bit of an art, frankly. I mean, but yeah, it's a bit of. I should say it's an art. It's something you get used to, but it's not sort of trivially obvious what are appropriate terms or not. But again, the two principles are minimalism and stability. Okay.
Yeah. Thank you.
Psi 6 does not change the T3 per half or LNT behavior.
No, it will not change anything at all, as a matter of fact. Yeah.
Yeah, I think that's
In this model, because this guy is already positive and stabilizes the free energy. Now, if this guy were going through a negative value, then you would have all sorts of time critical transitions and first order transitions and whatnot. It's a whole different ball game, and then you need the psi 6.
We had in laser induced spin.
You have exactly. That's right. They've used it. It's very common. As I said, there's this famous book on liquid crystals. I can recommend it to the students. One of the gurus of soft math is Degens. You know the name Degens? Okay, so there's a book by Degens, first by Degens, and the later version is by Degens and Prost. Prost is a senior collaborator of his on the physics of liquid crystals. It's a beautiful book, and it describes. It's all about Landau-Ginzburg theories for liquid crystals. And Degens made such fundamental contribution that in that field it's called the Landau-Degens free energy. So Ginzburg बेचारे का नाम हटा दिया और Landau-Degens हो गया. But Degens is a great man. It's okay. Huh?
Yeah.
Yeah. And single price. I mean, even no other shares. Okay. Any other questions online? Okay.
I think.
Good. So we meet at 11 tomorrow.
Okay, so let us thank Sanjay again. And we meet for the third lecture at 11 o'clock.
Yeah. And just one thing, I want to circulate a file. Who is going to take the responsibility?
Yeah, Deborah.